Welcome back, students. Now let's move on to the law of cosines. The law of cosines looks like this. Given triangle A, B, and C, that's an arbitrary triangle. It could be obtuse, it could be acute, it could be anything. Let's say capital A, capital B, and capital C represent the sides of the internal angles. And small a, small b, and small c are the lengths of their opposite sides. Please note that I made the color coding so that you can see this association better. For this triangle, we have this kind of identity. Small a squared is equal to b squared plus c squared minus 2bc cosine of capital A. That's for the angle capital A and the opposite side. The same is true for the angle capital B and the opposite side. Please note that all these, the highlighted part, are for the other two sides. And the same is true for the angle capital C and the opposite side, small c. Again, please note that this highlighted part is for the other two sides. In other words, even though we have these three identities, actually we are looking at just one, and the other two are just renaming all those characters. Now we're going to come back and prove it, of course, but we're going to make just one little observation at this moment. In a special case, for example, when capital A is equal to 90 degrees, then what is cosine of 90 degrees? Cosine of 90 degrees, or cosine of pi over 2, is 0. In other words, this highlighted part is 0, so minus 2bc cosine of 90 degrees is 0. Consequently, this entire highlighted part drops out. Adding 0 doesn't change anything. Now what do we have left? A squared is equal to b squared plus c squared. Haven't we seen this before? Yes, we have. That's called Pythagorean theorem. And that works for a right triangle where this angle capital A is 90 degrees. Now in general, the angle is not 90 degrees. In that case, we need this minus 2bc cosine of A. That's what the law of cosines are talking about. Now the angles are arbitrary. It works for not just A, but B and C as well. And of course, for different types of angles like obtuse triangles too. It's arbitrary. Now we're going to postpone the proof as much as possible because that's going to be a bit too theoretical. Let's move on to some applications. Here's an elementary application. Solving a triangle when three sides are known. A, B, and C are known. Now, we do not know any of those angles. So, the fractions, for example, sine of capital A over small a, that fraction is unknown. None of the numerator for the law of sine is determined. We have to use the law of cosines. And one way to handle that is to look at, let's see, in this case, let's find out the angle capital A. If you want to do that, let's move on to the first identity. And all those sides, A, B, and C, all these are known. The only unknown is cosine of capital A. So you can solve for cosine of capital A and take arc cosine. This is basically what I did over here in the solution set. Solve it algebraically. Let's get it in the same viewing window. Solve it algebraically, then cosine of A is the same as b squared plus c squared minus a squared over 2bc. And in order to find out capital A, simply take the arc cosine. Plug in the values and punch in the calculator, we get about 17.6 degrees. You can do exactly the same for cosine of capital B, algebraically solve it, punch in numbers, and then take arc cosine, and also cosine of capital C. Solve it algebraically, punch in the numbers for small a, small b, small c, and take arc cosine. The details are left to the students. Now let's move on to the other case. When, oops, I opened it up prematurely. When two sides and the angle in between is known. A triangle is uniquely determined by this setting, but again, we do not have an angle and the opposite side, so the law of sine will not apply very well. So what do? We used, well, the law of cosines, of course. And we know small b and small c and capital A. So which one do I use? Again, the first identity. Everything in the right-hand side is known, and all I have to do is calculate those by plugging those numbers. That gives me a squared. Take the square root, that's going to be my a. That's the computation I did in the first line in the solution here. Here. Did this computation and take the square root. Plug in the numbers, we have 13.2 units approximately. Now that we have all three sides, small a, small b, and small c, this is small a, small b, and small c, we can do exactly the same process before and find out cosine of capital B, and then taking the arc cosine, we get the angle. Cosine of capital C, we can take arc cosine, and we get the angle. Those are two typical cases to solve triangles. Now, do we have some further application? Okay, let's see. We have some time to do that. Go ahead. Here's an application problem. A tunnel is to be built through a mountain. To estimate the length of the tunnel, the surveyor makes a measurement as shown as follows. So we have the two sides, AC and BC. So in terms of the convention we have been using, small b is known to be about 388. And small a is approximately 212. And capital C is approximately 82.4 degrees. And are we ready to apply the law of cosines to figure out small c? That's the opposite length. Yes, we can do that. And we have just the right formula right over here. Everything in the right hand side is known. Left hand side is small c squared. After calculating out, just take the square root. It's an easy computation. Here it is. Plug everything in. And then use calculator. And then take the square root. We're going to have 416.8 feet, approximately speaking. I guess we have time to go ahead with more applications, so let's go ahead and do that. Two tugboats that are 120 feet apart are pulling a barge as shown. Find the angle between two ropes. So we have a triangle. 215 feet, 230 feet, and 120 feet. Three sides are known, and we are looking for an angle in between. We have just done this kind of problem before in the elementary exercise, example 3.3a here. Three sides are known, and then all you have to do is to find that angle, and set of cosine, find out the cosine, and then take arc cosine from the law of cosine. Well, here we go. Cosine of capital A is b squared plus c squared minus a squared over 2bc. Well, the same quantity because it's done algebraically. And all you have to do is take the arc cosine. Now, how about a, b, c, and values? Well, we are looking for capital A is the left-hand side point here in the barge. So small a is 120 feet, 20, and then the others are 212 and 230 respectively. Plug in all those numbers and calculate with your calculator. You're going to get 31.17 degrees approximately. Make sure your calculator is set in the radian mode. Okay, looks like we'll have time to do just one more. Estimate the distance between two kites. Well, we have two sides, 380 feet and then 420 feet. Let's call this small a and small b. And capital C is the angle, 30 degrees, if I make that kind of naming. And you can use the same rule as before to find out small c value by law of cosines, and then in the end we just take the square root. It's not difficult computation. Here we go. Now problem D is gonna be far more challenging, and I'm gonna just read and explain the problem, and I'm not gonna do this problem for you here. It's left to the students. A fisherman leaves his home port and heads in the direction of north 70 degrees west, as you see in this picture. So from north, we take 70 degrees angle toward westward. Travels 30 miles, so we have this second point, Egg Island. And we have another angle, north 10 degrees east. So from north, we take 10 degrees toward east and then travel 50 miles and reach Forest Island. And we have to answer two things. One is going to be a bit easier, and the second is going to be harder. The first question, find the distance between the fisherman's home port and Forest Island. In other words, you have to solve a triangle, basically. The distance between Forest Island and the home port, that's the unknown side of the triangle. The other two sides, 30 miles and 50 miles, are known. And if we know the internal angle at the Egg Island, then you can use law of cosine to determine the distance between Forest Island and home port. How do you figure out the angle? The internal angle at the Egg Island. I'm going to stop there and then I'll ask you the question. Find out the bearing from Forest Island back to the home port. That's going to be even more challenging, but I'm not going to tell you. Just go ahead and sweat it out. I do have a solution here in this notebook. Okay, one final application and then we're going to be done. 3.5, Heron's formula, and of course the proof of this Heron's theorem is not something we are interested in. It's kind of complicated, as you can see here in this proof. This is a truncated version actually, so go figure, this is rather challenging. And it kind of goes like this. S is half of the perimeter, a plus b plus c over 2. And according to that, we can find out the area of a triangle when three sides are known from this formula, which is called Heron's formula. For example, you can find out the area of this kind of lot by Heron's formula. All you have to do is plug in A is 125, B is 280, C is 315, calculate this half of perimeter and then plug everything into Heron's formula. You can name A, B, C differently, but as long as you cover 315, 280, and 125, you're going to get the same answer.